In this video, we're going to be talking about Pascal's triangle, and we're actually going to be constructing some observations about the patterns in Pascal's triangle. And in fact, we're going to prove one of the observations that we make about Pascal's triangle. All right, so let's take a look at Pascal's triangle again. Now, forget for a moment where it comes from. Just look at it as a mathematical object. What do you notice? Well, there are lots of patterns hidden away in the triangle, enough to fill a reasonably sized book. Here are just a few of the most obvious observations. Number one, all of the boundary numbers, all of the entries on the border of the triangle are all 1. Here's another observation. Any entry not on the border is the sum of the 2 entries above it. Number 3, the triangle is symmetric. In any row, entries on the left side are mirrored on the right side. And then number 4, and this one's a little bit more complicated. The sum of all the entries on any given row is a power of 2. Let's check this one. So if we add up all the numbers on this row, we get 1, which is 2 to the 0th power. If we add up all the entries on this row, it's 2, which is 2 to the 1st power. 1 plus 2 plus 1 is 4, which is 2 squared. 1 plus 3 plus 3 plus 1 is 8, which is 2 to the 4th. And if we pick any random row like this one, 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1, go, 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 that is 64. I did not mean to erase all of that. But the point is, they're all powers of 2. In this video, we will state these observations in a more precise way and then prove that they are correct. At least we're going to prove the 4th identity that we come up with, the 4th observation, which was the powers of 2. Now, each entry in Pascal's triangle is in fact a binomial coefficient. So this one right here, oh, there they are. This first entry on the top is actually just 0, choose 0. This entry right here is 1, choose 0. This entry right here is 1, choose 1. And if you pick a random one, that entry right there is 5, choose 4. 5, choose 4. Now, it's important to understand that the way we label the rows on Pascal's triangle is a little bit weird. The first row, the very top row, is actually row 0. And then the row underneath that is row 1. And that's just because these are all the 0 choose numbers. These are all 1 choose 0, 1 choose 1. It's row 1. This number right here, this row is row 2. So that's 2 choose 0, 2 choose 1, 2 choose 2, and so on. Okay, so now let's take a look at these observations that we made. And let's represent them with binomial coefficients. Let's start with the first observation that we made. The first observation was that all the numbers on the boundary are 1. Okay, so what does that mean? That means in any given row, n, if we look at the first entry on that row, it's going to be 1. And if we look at the last entry on that row, it's also going to be 1. All the entries on the boundaries are 1s. What was the second observation we made? The second observation was that any given number is the sum of the 2 numbers above it, so long as it's not a boundary number. Okay, so that means that, what does that mean? That means that n choose k, let me make sure I get this right. There we go. N choose k is going to be, well, if we wanted to compute that, we would just look at the row above it. N minus 1 choose k minus 1, and add that with n minus 1 choose k. That was our second observation. So that is another way of saying that any entry is the sum of the 2 entries above it. Let's take a look at the third observation. The third observation was that this was symmetrical. which can be written as n choose k equals n choose n minus k. So if we put a k equals 0, this says n choose 0 equals n choose n, which is technically what we found with identity 1. But it's also symmetric if k equals 1. N choose 1 is the same thing as n choose n minus 1. And then the fourth observation that we made is that if we add up all of the entries in any given row, it should add up to a power of 2. So n choose 0 plus n choose 1 all the way up to n choose n is going to add up to 2 to the nth power. Specifically 2 to the nth power. All right, so these are the 4 observations. Each of these is an example of a binomial identity. An identity involving binomial coefficients, meaning. Since we haven't really seen any reasoning behind the last identity here other than just some a random observation that I made, let's prove this using a slick trick. So how can we prove this last identity? Well, I'm going to need some room. So we're looking at the last identity right there. And then it likes to zoom out for some reason. I don't understand why. There we go. All right. So recall that, there we go. Recall that x plus y to the nth power we said was n choose 0 times x to the n, y to the 0, plus n choose 1, x to the n minus 1, times y to the 1, all the way up to n choose n times x to the 0, y to the n. So that was something about the binomial expansion of x plus y to the n. Now, this is true for all x and y, all integers x and y. If we plug in x equals 1 and y equals 1 into this, that means that 1 plus 1 to the nth power equals n choose 0 times 1 to the n times 1 to the 0 plus all the way down to n choose n times 1 to the 0 times 1 to the n. Now multiplying by 1 over and over again does nothing, so we can get rid of all these 1s. And then 1 plus 1 is 2. So that means 2 to the n equals n choose 0 plus n choose 1 plus all the way down to n choose n minus 1 plus n choose n. And that's the proof right there. Boom, we have exactly what we were looking for. That was a mathematical proof of why the sum of all the entries in a Pascal's triangle adds up to a power of 2. Wow, that was a lot. If you notice, we can actually pick many values for x and y, and we can make even more unique identities. By yourself, try plugging in, instead of both x equals 1 and y equals 1, try plugging in x equals 0 and x equals 1 and y equals 0 to construct a proof for the first observation that we made. Anyways, thanks everyone, and I'll see you in the next lecture.